So I'll start again. So it's my privilege to introduce Dr. Guiping, and she's the department head of the Department of Sustainability at RIT. Her research is focused on operations research and data analytics with applications in renewable energy systems, sustainable supply chain design, bioinformatics, and sustainable agriculture. Dr. Hu's research has been supported by a variety of agencies, as you can imagine, but she has been successful in attracting more than $10 million worth of funding, which is pretty significant, believe me. NSF, USDA, Department of Agriculture, Department of Energy, and DOD, Department of Defense. She received the Mid-Career Research Award and has been recognized as a Plant Sciences Institute Scholar at Iowa State University. She has published more than 75 journal articles, peer-reviewed, and 40 conference proceedings. That's also significant. So I think chasing that 100 number is always a good one, right? And she's closing in on that. So that's a very cool accomplishment. In addition, Dr. Hu is active in serving in the profession of industrial engineering, including as current president of the Operations Research Division and past president of the Engineering Economy Division in the Institute of Industrial and Systems Engineer, IISE, and as the vice chair of the Service Science section in the Institute of Operations Research and the Management Sciences, INFORMS. So it really is a privilege for us to have you here. As you probably heard this morning, she's new to RIT, and she has some distinct overlap in the use of imaging in terms of deep learning and so on, and also some imaging experience in terms of applications. So Goyo and I thought that it'd be useful for us to be exposed to her research and maybe look at potential interactions and collaboration with imaging science. So thank you so much for taking time.
Well, thank you for the nice words. Yeah. Well, it's my great pleasure to be here. Can you hear me in the back? Okay, that's wonderful. I assume you can hear online. If you cannot, then shout out. Okay, all right. So I thought today what I would like to do is basically introduce a little bit about my background, because you're a first year PhD student and then you're just starting your career. As we were talking over lunch, I like to share some of my experience. And I want this to be an interactive seminar rather than, oh, this is what I'm lecturing. So what I want to do is that I'll talk a little bit about my background, my experience, and then like broadly my research portfolio. Then I'll narrow down and I'll talk about our 3 projects that are currently going on related to imaging science and agriculture. And that can get some thinking juice going. And like y'all talking about, I love to collaborate. I think my career has basically jumped from one type of collaboration to another, and that has served me pretty well. So I want to do that in New York, at RIT, of course. So this is the building of imaging science. If you don't know, right? It's sometimes you're in the building, you don't know, wow, look like what's this building? So yeah, it's beautiful. And this is what my office is at. I'm in GIS, Golisano Institute for Sustainability, which is not that far away. It's about 2 minutes walk. So it's easy walk over if you want to have a chat. My schedule tend to be busy, but I always time for students, because that's what we are here for. We want to serve our students. So feel free to stop by, send me an email, we can chat. Okay, all right. Like I mentioned today, I like to talk a little bit about the type of data analytics and system optimization that has applied to imaging science and sustainability. I use that broadly defined because I represent sustainability, and this is, you know, the PhD program for imaging science. So like I said, it's very broad. I just want to share something I've done to get the thinking juice going. Some of you shared your research interest over lunch about you want to do deep learning, you want to do, you know, computer vision and all of those. Those are great. I think these are great topics that are related to what I'm going to talk about today. And I have to do one slide infomercial about my program because I'm the PhD director as well as the graduate director for our sustainability program. So I represent 2 academic programs, Sustainable System, that's a master program, and then PhD in sustainability. I oftentimes talk about sustainability as a very interdisciplinary program. We have faculty from, I'm from industrial engineering, we have chemical engineering, we have policy and energy related background. So it's basically a very inclusive type of discipline. Our curriculum tend to be very quantitative, and we have courses in industrial ecology, risk analysis. I'll probably infuse some of what I'm going to do research on data analytics and optimization in some of the courses. And then our faculty research are actually pretty broad, and this list can go on. And these are just to give you some examples. So those of you who are doing imaging science, I think it can be applied to a variety of application areas related to imaging science. For example, one current PhD student of mine, still at Iowa State, he was using camera to do the monitoring of the manufacturing process of a 3D printing. So that can be imaging science, right? You look at the camera and then you are trying to detect whether there is any faulty printing process. And if there is, how do you go by correcting that? Okay, that's one slide. Oh, it is really hard to hear for some reason. Can you hear me now? I don't know, because should I take my mask off, or can the online attendance? Oh, I can hear you very well. Okay, that's great. Okay, wonderful. So I have one slide to talk about my background. So like y'all mentioned, I joined August, literally about 2 months ago, and at IT. And I've never been to Rochester before this trip. So because my interview and everything were done online, but people are great. I feel welcome the first day on campus. My faculty are great, and I have great colleagues over there. Over the years, I have been going through the different ranks at Iowa State University. Iowa State is the only other institution I worked for after my PhD study, and it's been fun. As you can see, my primary appointment is in industrial and manufacturing systems engineering, but I do all kinds of other things. Like, for example, GPSA stands for Graduate Program for Sustainable Agriculture. BEI stands for Bioeconomy Institute, because we have an institute focusing on renewable energy, biofuel. And BCB stands for Bioinformatics and Computational Biology. So I'm affiliated with them. I can advise students in those disciplines. And then my education, I'm originally from China. So my undergraduate was in China. I did sort of automation, sort of between mechanical engineering and electrical engineering. As I shared earlier today, my senior design project was on speech recognition. So something that has some connection to the double. And then my master and PhD were from Pittsburgh. So industrial engineering is a very broad discipline as well. So basically we have operations research, statistics, system engineering, and some manufacturing systems. So my dissertation was on sustainable manufacturing and decision support tools for manufacturing systems. And I'm going to use the next few slides to talk about broadly my research portfolio. I'm not going to go to too much detail, but basically you can get a feel of what she has been working on in case you want to have follow-up conversation. And then I'll drill down to some specific topics related to imaging science. Yeah, maybe you can keep an eye on time and then remind me, oh, there is a clock there, wonderful.
I'll give you a 5 minute.
Okay, yeah, because I do a lot of work with professional society. Like I chair a lot of sessions, and that's something I'm good at doing as well. I'll give you 5 minutes warning, 2 minutes warning, and then time is up, you're done. Okay, so sustainability in supply chain design. So supply chain is really different entity that link from the supplier to the final consumer. So in this case, we are looking at raw material supplier going to manufacturer and then distributor, and then to the retailer and final consumer. So in this case, their product flow, information flow, and also financial information. The question is that, how do you integrate them together so that the decisions are made very globally optimally? So in this process, one thing I was focusing on is closed loop supply chain. So basically how you take the product and think about how do we make best use of it? And then how do we basically take care of the end of life so that it doesn't go to the landfill and it's doing harm to our environment. And in this process, there are a lot of decisions has to be made, a lot of data gets collected and all of those. And of course, these are all driven by mathematics because I personally don't do any lab work or field work, but I collaborate with people who do. And in this case, it's a supply chain design modeling that we did that has to do with multi-level optimization problem. And then this work is being supported by National Science Foundation, and also there is an industry and university consortium on Center for E-Design. All right, to basically elaborate a little bit on that is sustainability in manufacturing production. So this is a project that I did about 4 years ago in collaboration with John Deere, which is an agricultural equipment company, and then also Boeing, Boeing, right? So, and then what we were doing in this is basically there are a lot of information flow from the shop floor, working cell, manufacturing process, and there are a lot of information that gets disconnected. For example, when we were doing the current state review, the material acquisition was actually done by taking notes on a piece of paper. And it's not very efficient and effective because there are some action that needs to be taken on hourly or at least on a daily basis. So what we did was we designed a decision support tool to basically synthesize all those information and then provide decision support and then project it on the dashboard so that the shop floor supervisor or the material acquisition specialist can basically take that information and make informed action or decision. And then we also did some app on top of that. And this is being supported by a National Manufacturing Center. It used to be called Digital Manufacturing and Design Innovation Institute. Now they call them MXD. Switch gear a little bit to talk about sustainable energy systems. So I mentioned that after my University of Pittsburgh work, I went to Iowa State following my husband. Now, Iowa, anyone here from Iowa or close to the Midwest? If you go there, you'll see there is a whole bunch of corn and soybean, right? So after I joined there, I said, well, there's a lot of corn and soybean here. I want to do something that can help the farmer out here. So the first thing I tackled was biofuel, renewable energy. But I'm not a chemical engineer. I don't know how to do experiments. So one thing I did was I go out and talk to the mechanical engineer and chemical engineers, and then we start talking about collaborations. So something I did was we were looking at system analysis. So basically look at if we scale this. So they have done bench work. And what I have been doing, or my research group has been doing, is really scale that up to the commercial scale. We were working with DuPont Poet, and then so basically some biofuel company locally. And we were looking at if we were to scale this up, whether it is economic feasible or environmental viable. Okay, so these are a few pictures that I actually borrowed from a project that I did from Department of Energy. We were collaborating with Pacific Northwestern National Lab on some economic analysis for a new novel production pathway related to corn stover. And this is a facility down in Iowa. They were going commercial scale. Chat over here. Yes. Thank you, Manisha. Okay, so sustainability in energy systems. So this kind of reminds you of the closed loop supply chain in the agriculture sector. And some of you were asking about, well, a lot of you think, well, I'm everywhere, but at the end of the day, they are connected, they're similar. A lot of the underlying principles are similar. I'm basically using mathematical model, data analytics to help people make decisions. So in this case, we were basically looking at from the agricultural ecosystem, how we close the loop, how we really connect them and make sure they are consider all the factors that would impact the economic outlook as well as environmental impact. And then these are some of the tools we've used. Process simulation. So basically we use the bench scale data, scale it up to the commercial scale, and then their economic analysis, life cycle assessment, and also after you collect enough economic and environmental impact data, you can actually analyze, say, well, where's the best location to locate this type of facility? Because you need to think about where is your raw material from and who do you supply to, right? So there are optimization model about what's called location allocation and logistic problem. So it's actually a pretty fun project to work on. This is by, so that will fold into some sustainable agricultural and data analytics. So as I start to do more of the biofuel work, I get connected to my bioenergy and agricultural colleagues. And they start talking to me, say, hey, Guiping, it looks like, well, we have some other problem which we may use your expertise. So in this specific project is supported by Plant Science Institute at Iowa State. So basically what we are looking at is eventually we want to achieve superior phenotype. You can replace the corn by grapes or by apple, just whatever you're interested in the crops. But underlying principle here is that we are taking the genotype information, it's basically the SNPs and chromosomal information, and also the environment, soil type, weather information, and the type of microenvironment in the growing specific micro stages. And then the management is really things that you can control, like for example, irrigation, fertilizer application, right? When you combine those, then that will jointly determine your phenotype. So basically it could be yield, flowering time, how much you're getting per year, things like those, how big of year I'm talking about for corn. And in the data analytics, there are basically 3 levels. Really, there are 3 levels. Descriptive, you're trying to understand what happened in the past. What happened in the past. And then predictive, you're trying to you're trying to predict what's going to happen. Let's say we have historic data. We're trying to understand if the weather next year is going to be look like this, what am I getting out of the piece of land? And prescriptive, it's really the decision-making component. For example, what should I apply? What kind of fertilizer? When should I apply? Do I apply before the growing season or during the growing season? How much, right? So there are all kinds of interesting problems. And summarize a little bit over here. Yesterday, I was talking to a Cornell colleague over there on grapes, and they were basically talking about for grapes, when to trim, and then how much to trim, right? And those type of problems, and then canopy management. But to summarize, it's really a precision agricultural and optimization modeling problem. At the end of the day, you're taking the data you have handle on and trying to get insight out of it and trying to change this insight to some type of action. And that action with the modeling, you're going to be able to tell it's going to lead to some superior results. All right. I have to do my acknowledgement. The work has been supported by a variety of organizations. So Cortiva is a company and Syngenta is a seed company as well. And these are 6 of my PhD students who have been working on the project. And then these are my faculty collaborators. Pat Schnabel is the Plant Science Institute director. And Li Zhi, he's a colleague. And he happened to be my husband as well. So, and then Yuva is a scientist who have really helped out with data collection and educate me about how, for example, later on I'm going to talk about soybean sudden death syndrome, how really that symptom work. And then Darren is a faculty in the plant pathology department. All right, so with that, I'm going to talk about 3 mini projects that we have still going on in my research lab. And again, I just want to share this. Some of those we have paper published, some of them is really working in progress. So the purpose of this is really to share something we've done and get some thinking in terms of what the next project would be. Hopefully that can help some of you decide, well, actually we can work on agriculture or we can work on something related to optimization. Okay, the first one is a gated recurrent unit. This is basically a type of neural network based model for soybean sudden death syndrome with satellite imaging. And I don't know how much background you have for soybean. Okay, so what's that? Yeah, soybean is a staple in my household as well. So plant disease is a threat global food security. So it's a big thing. I'm not going to go into detail about the motivation because I want to leave enough time for discussion, and I'm going to mainly talk about the method. So basically, the disease are hard to recognize. The earlier you can recognize, the more options you have for treatment, for management. Okay, so it's variable in time and it's variable in space, and it's also variable by varieties, meaning this type of soybean is different from the other type of soybean. Okay, so just real quick, I'm probably preaching to the choir for the sensing techniques. There is thermography and then fluorescent and then hyperspectrum. I'm not going to go to the detail because in this specific research, we are not using this type of data. We're using satellite imaging because that's what we have access to. But I think if we have access to this type of imaging or the type of application I'm interested in, we can definitely apply similar techniques. I put it here so that we can have some connection to the audience here, right? Okay. And then, so the research question my colleagues and we were talking about is that, you know, soybean sudden death syndrome has been, people have been using near sensing. So basically it's a close look at the leaves, but it's very time consuming and it cannot be done at large scale. So now the question is that, can we use remote sensing data so that we can have a wider, you know, scoping of the disease? And of course, there's trade-off between accuracy and also the size of field you can analyze, right? Now, and that's what we are trying to go from near sensing to remote sensing. Actually, the second piece of work I'm going to talk about has to do with near sensing. Okay, so in terms of remote sensing, there's UAV. This year we are going to get some UAV data, but so far our data had, well, there are actually some tracked mounted tools as well. My colleagues, they are working on data collection, but in this specific work, we were using satellite imaging. So satellite imaging is not very high resolution, right? Each pixel is about, I think I have the number here. I believe now, Chrissy, on that, I don't remember the specific, I think each pixel takes about 3 meter by 3 meter, but I could be wrong because we have different 2 resolutions. One is 72 centimeter by 72 centimeter. But anyway, in terms of the workflow of the project, my collaborator, they collected the data, and then also they have disease data. They actually walk through the field and sort of use as the ground truth for analysis. And once we have the data, I'll try to stay close for our online audience, we have gone through data processing and also data visualization, because I realized for a lot of farmer collaborators, it's extremely important to display what is going on, what are you doing, and also the data analytics over there. The research data, it's from Iowa State University. There's some research farm there. We have 2 years of data and 6 imaging days and 6 inspection days. They are they try to really match them, but there may be 1 day or 2 of a difference. And to the right, you'll see there are different types of fields that we are looking into, and there are different locations, rotations, as well as locations nearby. Okay, so there is RGB and near infrared information collected, and then we compute the NDVI, and also there is rotation information. So like I mentioned earlier, it's not a very high resolution. Each quadrant means each of this smallest block here will just give us 6 to 9 pixel information there. So it's very limited information. And then the research method, we designed something called gated recurrent unit-based model, and we compare it based on XGBoost and fully connected neural network. I'm not going to go too much detail about the research method. This is basically a variation of recurrent neural network. It's time-stamped because we have 6 days for each year, and then we basically take that date information. And also for the disease, once there is disease, it's going to be disease for the rest of the season. So there is some time dependency to the sequence of the images. And just really quick talk about the results. We run different 4 experiments there. The experiments are designed based on conversation with our collaborator about how we split it, and then how basically we want to include enough variation so that the method really can cover a variety of scenarios we are facing over there. And the first row for each of the blocks over there, the first one is the method that we've designed, and the other 2 are sort of the benchmark out there. And as you may see, we have all lead to improvement. And you may say, oh, it's only 1%. It turns out that in this area of research, 1% is not a small improvement. It's very hard to make improvement. And we've actually achieved a little bit better than that for some of the lower range. So we are happy about, at least our collaborator, they're happy about it. And then we've done some extension work. Now with additional data of UAV and also tractor mounted data, the resolution will be much higher. With higher resolution, we can probably do much better in terms of the improvement because there is more data for you to play with. And then, but anyway, to conclude on this piece of work, we used a gated recurrent neural network, and then we compare it, and then basically we see some improvements. Okay. So with that, I'll pause a second and ask whether there is any questions out there I can help answer. Yeah.
Do you recall the spectral characteristics of the satellite that you used?
I do not.
Yeah, I'm just curious if it's probably more of a multispectral system, I'm guessing not a hyperspectral.
No, it's not a hyperspectral. No, it's fairly simple one. It's the data comes from the California company. Was there a company Planet Scope or something? I can look into that, but no, it's not, because this is satellite imaging, but as far as I know, it's not very detailed information. So it's not. Yeah. So, but if there are those data, we'll be happy to play with that and see. Yeah, but that's a great question. Other questions? All right, let me continue, and then maybe if you have any questions, feel free to yeah, go ahead. Yes, we have a USDA project that's still going on with my colleague, the far right, Darren Yuba. I believe we maybe have 1 more year in that project, and we'll see what we do after that. My student who is working on this project, he is going to graduate probably next summer. Yeah, but when I'm in Rochester, I need to figure out what are the exciting problems on campus, just like what I explored when I was in Iowa on corn and soybean. Here, I may now work on corn soybean because it's just but if there are data, we can continue work on that. But probably we can look at maybe apple or grapes. I'm sure there are a lot of things for me to learn, but that's what's making research exciting, right? And for you, researcher, either PhD or master, oftentimes, the process of exploration is the most exciting, but also most stressful from your research perspective. Saying, I don't know whether it's working out. So like I shared earlier, it's really important to think outside the box and keep your advisor in the loop. About, well, I'm trying this. Is it working? On things like those. But great question. Okay. Yeah. Yeah, you can go and then.
So far, talked about this research is related to plant agriculture. Do you see any potential for methods similar to this research being extended to say animal agriculture or aquaculture?
Great question. I do not have that included here. I do currently have a project that I'm working with an animal science professor. And this morning I was talking to a Cornell professor. He was working on dairy cattle. At this point, our data are not image related. That's why I have not talked about this. We were looking at feed rate and what type of medicine they were given, and then the type of environment this, and I would say I was working on pig, swine, and then here is dairy cattle. So, and then we were trying to look at how quickly these pigs growing. So basically, if you think about what I'm interested in, is basically input and output. And then there are all kinds of things we can do in between. But this conversation in the morning, we were talking about, well, maybe we can use video they were talking about using video to keep track of how this dairy cattle it's maybe moving around and their behavior of eating and then things like those. There will be similar things there, but so far I haven't done things related to that. Great question.
So I was just trying to think of another optimization, I guess, challenge. That would be like satellite imagery probably isn't super cheap. I know there's like digital globes and plant labs that have lots of satellites that have multispectral sensors on them. But is there a way to like optimize when a farmer should buy imagery for their farm and like during the season, and how often they would want to purchase that? And like, is there trying to basically maximize the benefit for them, where they spend the least but get the most out of information during the critical times in their crop cycle?
That's a great question. I was wondering about that as well. So far, I haven't done anything related to that, partially because we just don't have the data. In another project, we were working closely with farmers, but not on the data collection. They were interested in knowing because they were buying tractors. Now the question is that what kind of data collection system should I adopt? Because there is trade-off there, right? The more you have, obviously you have more information. But then, do I have it throughout the season? Do I have it multiple times throughout the year? So you're right, that's a very typical optimization model, optimization problem that can be formulated into a model. I haven't done that, but yeah, that's something that can be explored. That's related sort of precision ag, right? You're trying to figure out when to do what. That's the most efficient and effective. And I must say that there is trade-off. At a certain point, you don't want to overdo it, right? Because when you overdo it, when I say overdo it, I mean you just pile on all kinds of sensors and data collection tool. But that can tend to confuse, what am I really doing here? What kind of decision am I trying to make? So there's trade-off, and also, capital investment on the type of sensor they're using to collect the data. And same for the animal science too, because you can have all kinds of sensor in the animal house. Now the question is that, when should I collect? What should I collect? And then their storage cost as well, right? So, but that's a great question. That's an optimization problem for sure. I love this type of discussion. Yes.
So are you implementing the GRE-based RNN to like classify diseases into soybeans, or like or is it like a four? So how many diseases are you trying to predict?
That you're basically trying to get me to the second topic. In the previous one, soybean sudden death syndrome, it's just one type of disease, and you either have it or you don't have it. So there's just a 0-1. That's why it's a classification, but it's a not a multi-class classification. Okay, so with that, I'll basically transition to this one. This one is the image-based plant disease classification. You were jumping ahead of me, and then we used something called a generative adversary network or limited training data set. Okay, the reality is that the imaging processing literature is actually quite advanced when you're talking about deep learning, if you have enough training data, right? Because think about, you can do very, very high accuracy of classification if you have enough training label data. Like say, oh, this is a dog, that's a cow, and then if you have enough label data, you can achieve very high accuracy. But the reality is that it's not going to be enough training data, because oftentimes for agricultural, for a lot of plant disease, it's not cheap to have the label. It's easy to take picture, right? But now the question is that you need to have the human later to basically create labels that this is disease, that this is this type of disease, this is another type. Okay, so this is focusing on the limited training set. And that's in a way addressing your, so in this case, we have all kinds of disease. I'm not going to go into detail. So the research questions basically we are given is a near sensing. So it's very close, this picture. And then we need to classify, I believe they are, is it 50 some classes. I'll come back to that. But anyway, there are all kinds of disease we are trying to classify based on the picture of image. And there are different types of crops as well. So it's not just soybean, we're trying to classify into different images. It's different crops and different disease types. Okay, so I'm not going to go into detail in the interest of time. So this is basically convolutional neural network structure. There are all kinds of, advanced work in this area about what kind of structure and then what type of layers you should design for different types of applications. If you're interested, we can talk more about this offline. And this table basically shows if you have enough training image, it can go actually pretty high accuracy. Okay, so for example, if you have, in this case, there are different types of disease. That's what I'm trying to say over here. If you have enough image, the accuracy can be quite reasonably high. Now, what if the training data set is limited? And that's what we are facing in one of the projects, right? We just have them, for example, even for the one about sudden death syndrome for soybean, they can only go through the field 6 days per year, and they just don't have enough data there for you to really understand. And have we heard of overfeeding problem? Right, so this is basically what overfeeding problem is. If you have enough data, so the green curve is the ground truth. You're trying to approximate. When you have enough data, you're doing pretty well, right? But when you have limited, it depends on where your data is being collected. You can generate all kinds of curves, and then when you just have one point, it's just to get the problem worse. Okay, so this is called overfeeding problem. And then what we've done in this is through different venues. One thing we've done is called data augmentation. So if we don't have enough image, labeled image, we'll basically create more. So basically we're trying to fully utilize the information that contained in the existing limited labeled image. And there is rotation, like the 2 cute dogs, you can rotate it, and then you can scale it, and then you can put it into different contrast, or you can add a Gaussian noise to it, then that's a different data set. So that's one way to create additional data. And what we've done here is we use what's called generative adversary network. So basically, it's a new tool that you can actually generate additional image with the limited labeled training image you have. And you might be wondering, well, it looks like we're still using the image you have, right? Why is that better? It turns out that this, I'll show you the result. It turns out that through this process, we'll be able to improve the classification accuracy. Okay, so this is the generative adversary network. So it's basically you're using existing image, going through this framework to generate more images that's labeled, okay? And this is a data set we got from this website. We also did it for a smaller data set for our USDA project. And in this case, there are 14 crops, 26 disease types, and then this many images. And of course, with this many images, it actually can labeled image, it can achieve pretty high accuracy. Now, what we did was we generate another data set that's limited. So what if we just have, 5% or 2% of the original data set? So for each category, there are only about 10 to 28 images in the training. And then we're trying to see with the type of method we have, how would that impact the accuracy? So these are few things we've compared if we just use convolutional neural network or we use convolutional with conventional data augmentation method like the scaling, contrast, the rotation, or the proposed method that I showed in the previous slide on the generative adversary network. Okay, so 3 slides each on the training and testing accuracy. So if we're talking about CNN only, you'll see that the training accuracy is extremely high, right? Because we can have a very complicated network, and then this is basically a sign of overfeeding, right? Your training accuracy is very high, almost to 1, and then your testing is about 0.6. If we add data augmentation, like add the rotation, scaling, this will increase to about maybe 75, something like that. And then you'll see that it actually has quite a bit of variation in the process of training. And then this is our method. So it's going to be able to stabilize sooner as well as with higher accuracy. And this table basically summarizes the training and testing accuracy. As you can see, when we are reducing type of, well, basically when you use the data augmentation proposed method, your training accuracy reduced because you're making the trade-off between the training and testing, and then the testing accuracy is much higher comparing with the CNN only, because we're reducing the complexity of the neural network. Okay, so with that, any question before I quickly talk about another yield prediction? So did that address your question on multiple disease classification sort of?
Yeah, I mean, that makes sense. But do you think the harmonic or basically binary maybe the time step was important, I guess.
I think for that, it's mainly we're incorporating the time steps. It's less of just simply classification. Yeah, you're right. Because the main thing we were working on to incorporating, and I didn't show it in this presentation. We were basically doing prediction as well. This is what I showed here is basically descriptive analysis. We basically use historic data and understand if we have this picture, do we have soybean sudden death syndrome? Now, the next question is that if we see these 3 pictures in the first 3 inspection days, what are going to be happening down the road in the next 3 days? So it's prediction as well. In that, it's even more pronounced because there is going to be, yeah, it's context-based. Yeah, you're right.
Oh, one more question. So all that data you were generating and the results, you need to have all those annotated properly, right? So how are you tackling the annotation problem? Are you doing it manually or?
You were saying that the limited training data, right? Yeah, we assume that the label is already there. For each species, 10 to 20 of the labeling is not too bad. The question is that whether you can label hundreds of them or thousands of them. So you always need to have some label data. And we've used Amazon Turk to do the labeling. So that's a very expensive process. Automated labeling, you still have to use historic data to guide that process, right? So you always need to start from somewhere. Yes, that's how you learn. And that's what's called, that's basically something called adaptive learning and active learning. You're using historical data to inform the next step about data collection, about labeling as well. But yeah, did I answer your question?
Yeah.
Okay. Yeah, so quickly talk about this has not been published. We're still working on that. It's a transformer-based method for soybean yield prediction. And in this case, we are using time series images and treatment information, basically whether the type of crop is disease resistant, drought resistant, so it's different type of treatment for management practice. And the field image look like, so these are soybean. Okay, these are soybean. So it's also time stamped, right? I don't remember how many days throughout the year, but anyway, it's taking at a certain angle. That's another thing that we were trying to address, but this is an example of a field image, and it's taking a few times throughout the season. And these are seed treatment. I'm not going to go to details. It's basically different types of seeds with certain type of chemical treatment about the seed characteristics. And then typical CN, you can get to yield pretty nicely as well. And what we are doing is basically when we have the picture, we can use what's called a vision transformer. What this is basically doing a projection based on some locational information. In the interest of time, I'm not going to go into detail on this, but the structure we are incorporating is you can use the locational information, but you can also use timestamp information. In this case, we have 3 dates, but you can have more dates as well, as you can see the dot, dot, dot. So basically you have the 3 dates, taking the image from the field, and then you use this vision transformer, use the time information to incorporate that information through the vision transformer architecture that I showed in the previous slide. And then you generate date 1, date 2, date 3 features is basically a vector that you generated. And then you use this to go through another transformer that's similar to vision, but it's not using location as one of the features. Is basically use the timestamp. And then you combine this to get the image features, and to the right, you have the treatment feature that goes through the typical fully connected neural network. And then through that, you can get the yield prediction. Just one quick slide to talk about the comparison. So this is our proposed method, and tested MSE is least square error. So the smaller, the better, right? You're trying to reduce the error. So the average is, it's really a baseline. That's what the farmers sometimes they most times they don't have information. That's what they're using. This is CNN, and this is non-time series convolutional neural network. So as you can see, our proposed method can increase. We are still working on that. It's a working in progress. I would say this is not fully optimized in the parameter tuning and a lot of other things. No, this is a least square error. So you need to take the square root, and then, yeah, you need to take the square root. This is square. So you need to take the square root, then that's, I don't know whether it's tons per acre or bushels per acre for this. I need to look into that. Like I said, it's still very raw. I literally just got this data yesterday. We were just talking about this. And when you dive into the method, I tend to forget the unit. Yeah.
The treatments were resistant to drought.
resistant to drought, and also there are different species as well. Drought, and then also there are some disease resistance as well. With that, I'll stop. And like I said, you know, the discipline of data science and optimization, we are basically trying to turn data into information and information into insight. And what I'm going to add is that we want to turn insight into action and into optimized action. And with that, I'll stop and use the last few minutes to answer any questions you may have.
Thank you very much.
Yeah.
Any questions for Dr. Wu?
One question, those papers, are you using field data like field images or like, you know, close-up photos, close-up images of the leaf? How are you doing that?
You're talking about the last work?
The first two.
The first one is remote sensing. It's satellite image. It's basically just 6 to 9 pixels. It's very, very coarse.
And the second one?
The second one is close. It's a,
Is it close one? Yeah.
I don't remember the resolution, but it's close.
Okay, so like my question is like, can we, you know, use the data that we train on a close, you know, like a high resolution image of the leaf, and then use it on a field image with a low resolution, like the leaves are gonna be low resolution.
I see what you're saying.
Yeah,
Well, it depends. At the end of the day, basically you're changing the input, right? You're changing the vector size of the input from a longer vector to a shorter one, or from the shorter one to the longer one. When you have more data, you tend need to update the structure of the model. And I cannot tell whether you can. My suspicion is that you cannot directly just apply it. And it's really important to consider the specific situation. And I wouldn't advise people just use what you trained in another setting, like different resolution to another one that you have not touched. Yeah.
I have a different question, Mary. So when we reached out to folks doing deep learning, say we want to do disease classification, there's a bunch of image transforms that the imaging scientists apply from something as simple as principal components, converting a time series into frequency components and so on.
Yeah.
But the response I got back from them is no, the deep learning algorithm needs to figure out the relationship between the training data and the output. We shouldn't do any transfer. But so your middle project to me looked like you didn't do significant transforms. I mean, these are rotations or scaling, but in a sense they're also transforms of the image. So what is your feel on saying feed it not only the original perspective image, but also feed it the principal components and feed it the etc.
I've actually tried using principal component. My collaborator tend to respond, say not to do that. But the middle one I was talking about earlier is really enlarge the data set rather than adding the feature. So basically what you're talking about is adding features. So it's a different problem. The middle one is trying to address, I only have 10 images of the labeling. Can I make best use of the 10 image by generate some more labeled image, although it's still from the 10, but by comparison, you can tell that it's actually can achieve better accuracy because that's a slightly different problem. PCA and other type of pre-processing, we've done that. I think if you have enough data, I don't think you need to use the PCA for that. The reason is that when you use PCA, you reduce the unit. You basically lost the unit, right? You're basically doing linear combinations of the input. Now, instead of saying, oh, the input of this feature, the importance of this feature, you are basically showing the importance of the combination of these features. So it's hard to understand the causal relationship. And some of the, as you know, some of the collaborators, they're really interested in knowing, what does this mean? What can I do, right? Yeah.
Other questions? Anything from online? I didn't check the chat maybe.
I think I have done a good job.
another question about, like, can you just give me an idea as to like how, how many features can disease have? Like, like in my head, it's basically, okay, one disease turns the leaf red or something like that. It generates a patch, like I'm just assuming why can't we use image processing, simple image processing and not CNN. Like CNN works better if we have a large user space, right? So that's what I was.
So when you say simple method, what are you referring to?
Like simple method as in, just do simple image processing, like a segmentation.
Oh.
Yeah.
Mhm.
So, okay, so this segmentation pattern of this disease is like this, and segmentation pattern of
Yeah.
another disease is something else.
Okay.
So instead of using CNN, where the features that are being learned is a black box to us,
Mhm.
we can just have a better handle on what features we are.
That's a great question. And one criticism for CNN is the black box, non-transparency, and not able to explain. And one I haven't shared in this talk, one thing we were trying to do what's called explainable AI. And what you are talking about can be one step towards that. So basically you can do either as a pre-processing of the steps, you can generate some feature that can, if of course, if you know, say this type of disease is going to have this round shape, like a red dot or something, and then it's going to have multiple. So if you have that insight, you can use that as a pre-processing before you feed into a more complicated method. Now, the more complicated network, what this can do is it can actually help us understand some of the underlying principle that we may not know yet, right? Let's say you know this type of disease, let's say sudden death syndrome. Right now, we just know the leaves are yellow out from the middle and gradually to the edge. But what if it's actually there's some other underlying, say maybe the edge was going to be curly, or I'm just giving you examples. Some of this you may not know from the agronomical background or insight. And by using data, so this is sort of a hybrid approach. And one of my paper I haven't talked about here, it's basically doing a hybrid approach, data-driven and physics-based. So data-driven is purely you're just using data. I don't care about what the physics tell me, but that can be very dangerous. Let me put it that way. So what we were doing is basically integrate them. Say I have some physics-based model. Like for example, when I do yield prediction, we have crop growth model. I know that with enough sunshine, this is how much biomass it's going to get accumulated. And then this, I can use this to generate some feature that can help feed into this model that can sort of improve the transparency, if you will. Yeah. I know trade-off. Yeah.
Yeah, but I mean, to your point, the type of symptom that you refer to is very much dependent on spatial resolution.
Mhm.
And I think one of the benefits of AI type approaches is that, like in the satellite example, you can take it integrate 3 by 3 little pixels for argument's sake. It's still detangle what it used to be sick for the plant. Whereas if you and I look at that 3 by 3 little pixels, no way we can see what it is.
That's right. That's right. That's right.
Also part of the problem.
Exactly. Yeah.
Well, thank you very much.
Well,
I just want to finish up and say, Dr. Nathan Williams is online. He looks at distributed energy systems, especially in third world countries, developing countries. So how do you optimize the distribution of energy in terms of the supply, the demand, things like that? And they often need to give you images to look at. Just a simple example, nighttime lights. In terms of where is our energy being used, should it be more used, where do you have big population centers, but no nighttime light prevalence. I'm using my own example. You might be shaking to say this what I've just described, but so there are a bunch of folks looking at imaging science solutions or imaging solutions that I really encourage you to look into the ball line of IT. And folks like Dr. Wu can actually serve this discussion we had this morning on your committee, given an insight into deep learning and the coupling to imaging and your problems. So you should really think outside the box when you and your advisor discuss the recommendation. Don't just pick easy, quick, move on. Think folks that can really
I'm not
contribute
very
to the
hard. I'm not very hard.
Was it? No, you know what I'm saying. It's
Yeah,
easy-
I was just kidding.
It's easy to choose the people close to you and the folks in the next door office and move on. But I really encourage you to think about that.
So in terms of master's thesis, so I know the minimum is 3 faculty.
So I'm going to stop you there because I want to wrap up this because it shouldn't be really part of our reporting and so on. But I'll answer your question offline in a second. Sure. Thank you very much. For your
Yeah,
time.
yeah, I enjoy this. I just show up in your building more often, so you know where to find me, and then we can start working together.
Thank
Well,
you.
thanks for the invitation. Appreciate the coordination and everything.
Thank you.
It's a lot of work. All right. Thank you for our online participants. Have a great day.
Yeah.
Bye.